All right, let's get started. Before we start today's chapter, let's do a quick review, recap some ideas. So first thing we need to make sure we have clear in our minds for this chapter is the 4 rules for a derivation that we have so far. So we have rule P, rule T, rule CP, and rule RAA. Rule P was the rule that, what did rule P allow us to do?
Rules of what? Okay.
The rules of derivation. If I were writing some derivation and I put something here and then I said, and that's by P, I would have put like line 1 like this. What did rule P mean there? So rule P says that we can introduce a premise at any point in our derivation.
Yeah.
Now does rule P. Okay, we remember what rule T is.
This was. So you're introduced premises.
Rule T is a rule for tautologically implied. If I have line 1 and line 2, and together they tautologically imply something, I can introduce that line 3. And I'd say that this was tautologically implied by line 1 and line 2.
Okay.
And then we have the rule conditional proof. This was our rule that said you can remove a premise. If I can show, remember fancy P, that's shorthand for the conjunction of all our premises. If I can show all my premises and some antecedent alpha, some statement alpha imply beta, then I can conclude from just my premises that alpha implies beta. I can go from this to this. That's what CP says. So I introduce alpha as a premise, show that implies beta, and then I get rid of alpha as a premise. I say, okay, so now just my premises I initially had tell me that alpha implies beta. Okay? This is equivalent to when you're doing some proof, and you're supposed to prove if x is even, then 2x is also even, or something like that. X is even would have been your alpha, 2x is even would have been your beta. And you say let x be even, and you show that implies 2x is even. Therefore, if x is even, then 2x is even. So you go from this to this. So common proof tactic in mathematics. Okay, and then the last one was the rule RAA, reductio ad absurdum. If I show my premises together with alpha implies a contradiction, something that is obviously false, then my premises must imply not alpha. If it was impossible for alpha to be false, if alpha being true is impossible, then alpha must be false.
Or what about the premise being false?
We're assuming all our premises are true. So if all your premises are true, or all your premises are consistent, and then you throw alpha in there and you get a contradiction, then that must mean
Alpha's false.
that your premises imply alpha is false. Because if it were true, then we get a contradiction. Okay, so this is another rule that allows us to remove a premise. So this lets us add a premise. This is typically what we do to derive new lines, and then these two enable us to remove premises. Okay, so those are the rules we've had so far. And now we're basically going to be introducing 4 more rules on top of that. Today just 2, and then next week another 2. And those are going to be the rules for introducing and removing universal quantifiers, and the rules for introducing and removing existential quantifiers. And then those 8 rules will pretty much be our rules for derivation in general. So today we're going to focus on adding 2 more rules here. the rule of universal specification and universal generalization. We'll just be using the universal quantifier today.
What are these rules called again?
This one is universal.
What is all of them together? What's the general name?
Oh, what are they called? These are our rules of derivation.
Oh, yeah.
Our rules of derivation. Our rules of proof. If you're going to prove something, you have to follow these rules. Okay. So that was going back 2 weeks. Now going back to last week. Last week we were largely focused on how do we symbolize sentences. How can I look at a sentence and understand logically what that sentence is saying? Look at its logical structure.
Yeah.
Determine the structure of a sentence. And one that we did a lot with was everything is red or not red.
Okay.
You remember how to symbolize that?
For all x,
For all x,
it's r applies to x or not r applies to x.
perfect. R applies to x or not R applies to x. And so that's what we focused on last time. Was going from some English sentence to break it down to its structure. Getting the structure of the sentence. Perfect. Okay, so with that, we're ready. We're ready to start doing proofs now with the universal quantifier. Intuitively, here's pretty much how these proofs always work. Step number 1, you symbolize your premises, the same way that you just barely read this and we symbolized it. Do that with all your premises. That's just using what we did last week. Step 2, get rid of all your universal quantifiers.
Universal or
Yeah,
not existential?
we're not going to be dealing with existential quantifiers today. So today's just universal quantifiers. So step 2, drop your universal quantifiers. Get rid of them. See what the statement says without the universal quantifiers. Then using those new statements, apply the rules we have here, the same way you always have, to come to your conclusion that you want.
Okay.
Then put the universal quantifier back in. That's roughly what this is going to look like. And rule US is going to be our rule for getting rid of the existential quantifier. That's what we're going to do here. And rule UG is our rule for adding back in the the universal quantifier. Sorry, if I say existential, I mean universal.
Okay.
Just universal quantifier today. So first we'll do an example using all these rules so you can see it in action. And then we'll define what everything is and try to give you good intuition for it. So first, just an example. So this example here. All animals are mortal, all humans are animals, therefore all humans are mortal. That's what we're going to prove. Good? All right, so let's get started with it. Line 1, what am I going to write?
Symbolize premise, so for all x.
For all x,
We're symbolizing each premise. So
yeah, I need to symbolize this sentence right here. All animals are mortal.
That's just one. Okay, so for all x, if an animal applies to x, would you do that?
Yeah.
So animal applies to x implies mortal plus x.
Perfect. This is, we can justify adding this line with rule P. Rule P says we can add a premise at any point, and this line only depends upon itself for its validity. If 1 is true, then this is true. If line 1 is true, this is true.
I remember this here.
Okay, let's go on to 2. What does 2 tell us?
For all x, h human applies to x implies animal applies to x.
Again, we justify that with rule P, and this line is true if line 2 is true. Okay, now what?
Now t is tautological. Do we need to use that?
Right, so now we have our premises, so next we're going to do the drop the quantifiers bit.
Got that.
Here's the intuition for drop the quantifiers. This says for all x, if it's an animal, then it's mortal. We're now going to say 3, ay implies my. That's how we're going to write it. AY implies MY. And the way we think about this is now we grab an arbitrary Y. We say, now for some arbitrary Y, if it's an animal, we know it's immortal.
Isn't that what X was? Just arbitrary?
No, X was any.
Oh, yeah.
Or every. This is saying, for all X, if it's an animal, then it's immortal.
Okay.
This is saying, now grab an arbitrary Y. And if it's an animal, then it's mortal. This in math is where you would say something like, let X be an integer. Then da-da-da-da-da-da-da, where you picked an arbitrary thing. So when we're trying to prove something about all integers, then the way that you would start that proof is, let X be some integer. You grabbed an arbitrary one. Y is an arbitrary thing. So we're not saying this for everything, we're saying for some arbitrary Y, this is the case. Now, this is using rule universal specification. We're specifying a particular universal, an arbitrary one, but now we're talking about one thing.
Okay.
So it's the universal specification on line 1. And this depends for its validity upon line 1.
Not line 1 and 3?
Now, this is true if this is true. If it's true for all integers, let's say the naturals. If it's true for all naturals that they're greater than or equal to 0, and you grab an arbitrary natural, you can still say it's greater than or equal to 0. Whatever you could say about all X, you can say about a particular thing. If it's true for everything, it's true for a particular thing. So that's the rationalization for concluding this from this. If it's true for all, it's true for a particular. An arbitrary one. We don't know which one, but if you've given an arbitrary one, you know it must be true. Similarly, for line 4 now, we're going to do the same thing. We're going to say for that arbitrary Y, if it turned out that human applied to that arbitrary Y, then animal also applied to that arbitrary Y, whatever it was. This is using universal specification on line 2. It's true if line 2 is true. Only depends on line 2 for its validity. Okay. So now that was drop quantifiers, essentially.
Okay.
Now we use the rules of logic like we've been using this whole time. If I know H applying to Y implies A applies to Y, and I know A applies to Y implies M applies to Y, what do I know?
H, Y, plus MY?
Yeah. If this implies this and this implies this, then this implies this. So 5. I now know if human applies to Y, then mortal applies to Y. That is tautologically implied, we're using rule T there, by lines 3 and 4. And now this is only true if lines 1 and 2 are true. Okay?
You only use premises on the right side brackets, right?
Say that again?
The only numbers in the right side brackets are going to be premises, right?
Yeah, these are always premises. Because the validity of a tautology is always, it's a tautology, it's always true.
Yeah, I was just wondering for a minute why I didn't put 3 and 4 in there too.
Okay, yes, always just premises. All right. So now we did this, we applied these rules as we needed to get to our conclusion. Remember, what are we trying to show? We're trying to show, therefore, all humans are mortal. I just barely showed that for an arbitrary thing, if it's a human, then it's mortal. And if I know that's true for any arbitrary thing, 6, then I know that's true in general. So I can now say for all Y, if it's human, then it's mortal. And that's the rule of universal generalization. And we did that to line 5. And this still depends on 1 and 2 for its validity.
Pretty simple.
Pretty simple. But crucial that you understand the individual rules that we're adding. And the rationale for it. Going from here to here, the thinking is, if it's true for everything, it's true for an arbitrary thing. Going from here to here, we're saying if it's true for any arbitrary thing, then it's true for everything.
Why do you drop quantifier in the first place?
Why do we drop our because these rules didn't tell us how to do anything with quantifiers. In particular, we didn't really know how to talk about tautologies with quantifiers. So these rules did apply when we had quantifiers in them. And we want to use those rules. Okay, so that was this example. Now let's nail down exactly what rule the rule US universal specification is. If a formula S results from a formula R by substituting a term Y for every free occurrence of a variable X in R, then S is derivable from, for all X, R. Bit of a mouthful. So let's do this with an example. So S, so looking at this one really quick, this is saying for all X, if it's a human, then it's an animal.
Okay.
And we're saying that this rule enables us to derive from that the fact that if John Adams is a human, then John Adams is an animal.
Okay. Yeah.
Okay? So over here, this piece right here is our R.
Is there a reason you did HA and HA instead of HA and AA?
No. Thank you.
Okay.
Yeah. A little a. Okay. So little a here stands for the particular John Adams. So if we know that for all X, if it's a human, then it's an animal, we're able to conclude that if John Adams is a human, then he's an animal. Let's see how this comes from this. So R is going to be just this piece right here.
Okay.
S is going to be this thing over here. If a formula S results from a formula R by substituting a term, in this case little a, for every free occurrence of a variable X in R, remember, if we're just looking at R, so that's without that quantifier, then the little x's are both free. In just this, if you just look at HX implies AX, X is free, X is free.
Yeah.
If I add for all X, HX implies AX, then it's no longer free.
Yeah.
So remember, R is just our formula this. So R is just this. So X is free in R.
The S.
No, this is S.
Yeah, that is S.
R is this formula.
Yeah.
That's what I've written here. This is R.
Oh, that is R, yeah.
Okay.
What's the quantifier though? Oh, R does not use.
R is not using the quantifier.
Okay, I see that.
Okay. So, if a formula S results from a formula R by substituting a term, in this case little a, for every free occurrence of a variable X in R, notice that both those X's are free in R. We're ignoring that quantifier for now. So you're just looking at that.
Okay.
Then S is derivable from, for all X, R.
Okay.
All right, let's do another example, labeling our R and our S, where it's a little bit more complex. An axiom from arithmetic. We know that for all X, X plus 0 is equal to X. That's an axiom from arithmetic. This right here, X plus 0 equals X, is going to be our R, just this piece.
Can R ever have a quantifier in it?
It could.
Okay.
But in order to use this rule validly, we would only replace the free occurrences of some variable. Okay. So, and then each of these is going to be an S. Bunch of different S's. Bunch of different things we can conclude from knowing this. We'll start on this one. Here's our first S. So in R, over here, notice that both those X's are free variables.
Yeah.
Okay. So if a formula S results from a formula R by substituting a term, in this case 3 is our term, by substituting a term for every free occurrence of a variable x in R, then S is derivable from, for all x, R. If I know it's the case that for any x, x plus 0 is equal to x, then I know that 3 plus 0 is equal to 3.
That makes somewhat sense, yeah.
Let's try a slightly more convoluted example. So now this is going to be our S. So, if a formula S results from a formula R by replacing every free occurrence, or by substituting a term, in this case, what's the term we're substituting? Y plus z. I'm substituting y plus z in for x. A term y for every free occurrence of a variable x in R, then S is derivable from for all x R. Notice that x, y, and z here are still variables. So, if I know that for all x, x plus 0 is equal to x, then I know y plus z plus 0 is equal to y plus z. That's something I can conclude from this. And then similarly, I can plug in some combination of constants and variables. If I know for all x, x plus 0 is equal to x, then I know x plus 3 plus 0 is equal to x plus 3. Okay, so there's a bunch of different instances of just using this rule. Trying to get comfortable with it. Okay, now the weirder rule. Universal generalization is a harder one. Before we get to it, we need a definition of something called a flagged variable. This is going to be one that's weird until you see some examples of it. But a flagged variable is a free variable introduced in a premise. Sounds kind of weird. You'll see why this is important in a sec. And the rule of universal generalization says that from a formula S, we may conclude, or we may derive for all x, S, provided that x is not a flagged variable in S. So we'll do an example where we use universal generalization in a good way, and then I'll show you how we might use it in a bad way, and why this flag thing is so important. And then hopefully that clears things up. So let's do this next two examples and then go back to it, and hopefully it makes sense after that. So starting with this one. What's the first thing we're going to do? Maybe I'll just read out loud real quick. No ducks are willing to waltz. No officers are unwilling to waltz. All my poultry are ducks. Therefore, none of my poultry are officers.
Okay.
All right, so let's try and put that one together. No ducks are willing to waltz. How do I say that?
For all x, duck applies to x,
Duck applies to x.
applies, waltz does not apply to x.
Yeah, not waltzing applies to x. Willing to waltz applies to x. Perfect. This is a premise, and it only depends upon itself for its validity. Okay, next, 2.
For all x, if officer applies to x,
If officer applies to x, then
then,
willing to waltz applies to x, right?
yeah.
That's a premise, only depends upon itself. Okay, now what?
For all, 3 again for all x.
So 3 for all x.
If P applies, poultry applies to x,
If being my poultry applies to x,
applies duck applies to x.
then being a duck applies to x. That's also a premise, only depends upon itself. Right?
Yeah.
And maybe let's write the conclusion to the side just so that we know what we're trying to prove. Therefore, none of my poultry are officers. We're trying to say for all x, if being my poultry applies to X, then not being an officer applies to X, right? That's the conclusion we're trying to get to. Okay, so let's try to get there. So, what are we going to do first?
Drop quantifiers.
We can drop the quantifiers first. Let's see. Okay, yeah, that's how I did it first here too, so that's fine. Okay, so first we'll drop the quantifiers. The first time I did this, I picked a different variable y. So maybe let's stick with that convention for now. So for an arbitrary thing called y, if duck applies to that y, then not willing to waltz applies to that y. And 5, if being officer applies to that y, willing to waltz applies to that y. 6, if being my poultry applies to that y, then being a duck applies to that y. This is universal specification on 1. This is universal specification on 2. This is universal specification on 3. This just depends upon line 1. This just depends upon line 2. And this just depends upon line 3. Okay, so we got all that. All right, now where do we go?
Laterals. Wy implies wy. Wy is implied by oy. So py implies not oy.
You're making it kind of hard for yourself. 7. We introduce as a conditional premise P of y. Assume y is my poultry. This is a premise.
Okay.
I introduce it as a premise. It's a premise that we're ultimately going to get rid of before the day's over.
Isn't that already introduced?
No, we did not know that being my poultry applied to y.
Well, there's a poultry in that.
Alright? Now, I'm going to put over here, this just depends upon itself, 7. And after 7, I'm going to put a little y there and end it like this.
Why?
Because y is a flagged variable. Notice that what it said, what a flagged variable is. A flagged variable is a free variable introduced in a premise. This is a premise. That's a free variable, so it's flagged. I cannot use rule UG on a line that has a premise with a flagged variable. So I cannot conclude from this, I can't make my next line, therefore everything's my poultry.
Okay.
That would be a bad conclusion. I can't conclude, if some arbitrary thing is my poultry, then everything is my poultry.
Okay.
Okay, so now, if P applies to Y, what do we know? If Y is my poultry, then Y
Is a duck.
is a duck, using 6. So then being a duck applies to that. This is tautologically implied by 6 and 7.
We already knew that. By 6.
We knew that if Y was my poultry, then it was a duck. Now I said, assume Y is a poultry. Y is my poultry. Well, yeah, then we know that Y is a duck. And we'll keep working with it. So this is tautologically applied by 6 and 7. So now this is true only if premises 3 and 7 are true. And after 7 we write Y to remind us that Y is flagged in 7. So I still can't use rule UG on this one. Okay, next, what do we know?
You know view of y is true. We're trying to prove
Yeah, if I know Y is a duck, what else do I know about Y?
that it, well, it doesn't bounce.
That it's unwilling to waltz. So then I know not willing to waltz applies to Y. This is tautologically implied by 4 and 8. And now this depends upon premises
1.
1, 3, and 7, where y is a flag variable in 7.
Okay.
Right? Now what?
I'm not sure how to get that O on that side.
Well, we know that if alpha implies beta, then from contrapositive we know not beta implies not alpha. That was one of the many rules of logic that we derived, that this is logically equivalent to this.
Oh.
So if I know being an officer implies you're willing to waltz, then I know not being willing to waltz implies you're not an officer.
Yeah.
So if you're not willing to waltz, we now know that you're not an officer. Not officer applies to y. And we know that from line 5 and 9. So this is tautologically implied by 5 and 9. We are now using premises 1, 2, 3, 7, and y is a flag variable in 7. Now, 11, I can use my rule of conditional premise. Therefore, I now know P applying to y implies not being an officer applies to y. I know this implies this. That is using the rule of conditional proof from lines 7 to 10. And now that enables me to eliminate 7 as a premise. I am no longer assuming line 7 is true. So, over here on my premises, I got rid of 7. So now we just have 1, 2, 3. Notice that none of our premises have a flag variable. So now I can use universal generalization. So 12, I can now conclude that for all y, if being my poultry applies to y, then not being an officer applies to y. This is using rule universal generalization on line 11. And it only depends upon 1, 2, and 3. And we're done.
Why did you have to create that premise? Line 7. Why can't you just say P of y implies D of y, so P of y implies W of y, and go from there?
You could have kept working at it that way. It's just, that's kind of a hard way to think about things. When you're trying to prove the Pythagorean theorem, you start out with, let triangle ABC be a right triangle. And then you show some conclusion. And so then you say, okay, so if it's a right triangle, then a squared plus b squared equals c squared. It's really hard to say, notice that if this were a triangle, then you could notice this. And that if you knew this, then you knew this. It's much easier for us to think about, let's just pretend it's a right triangle for a second. Let's just pretend that we're talking about something that is my poultry for a second. Okay, then it's not an officer. Okay, so I know if it's a poultry, then it's not an officer.
Okay.
So we could have probably gotten away with it in a simple proof like this. But obviously, as we get to more advanced systems, it becomes harder and harder to think about that way. And obviously, this is prep to prepare you to work with more complex mathematical systems. All right, any other questions on that proof before I erase it? Cool. Now I'm going to do a bad proof. So bad proof now. One, I'm going to introduce as a premise, human applies to y. That's a premise, and it only depends upon itself. Two, I'm now going to use the rule of universal generalization. So now I'm going to say, for all y, human applies to y. This is using universal generalization, and it just depends upon line 1. Now using line CP, rule CP, I can say, therefore, if human applies to anything, then for all y, human applies to it. This is using CP, and we just barely eliminated one as a premise, so this depends upon no premises. So in other words, I'm saying it's always the case that if something's a human, everything's a human.
Okay.
This is obviously wrong.
Yeah.
It is not true that if something's a human, everything's a human. But that's what I just proved.
Yeah.
I cheated. How did I cheat?
Flag variable.
Flagged a variable. Y is flagged in this premise. This is a premise with a free variable. So after this one, I have to put a y. Now I just barely tried universally generalizing on a flagged variable. Notice what this says. From a formula S, we may derive for all x, S, provided that x is not flagged. Here it was flagged, so I cheated. That's how I prove something invalid. I broke the rules. That's the only way you can ever prove something invalid. You have to break the rules to do that. The rules don't let you prove invalid things. So, let's read these two one more time, and then hopefully you're comfortable with them. So a flagged variable is a free variable introduced in a premise.
Yep.
And then from a formula S, we may derive a formula for all y, or for all x, S, provided that x is not a flagged variable in S. So we cheated here. In the other proof, we didn't cheat. Any questions on that? Cool. So now, let's switch to our next example. Where we're going to use universal specification except for on a particular object this time. All right, so first off, line 1, what does it say? I'll read out loud first and then we'll talk about it. No Episcopalian or Presbyterian is a Unitarian. John Adams was a Unitarian. Therefore, he was not Episcopalian. Yeah, that's what we're proving. So how do we symbolize our first line?
For all x, if E applies to x,
If, what'd you say, E?
Epis-
If being Episcopalian applies to X,
or
or being Presbyterian applies to X, then
not E applies to x.
not being a Unitarian applies to X. Right? Now, 2. Oh, sorry. This is a premise, and it only depends upon itself for its validity. Okay, line 2. What's our next premise?
That's not a premise.
John Adams was a Unitarian.
Yeah, it's just not quantified.
Yeah, it's not quantified.
So J,
We'll use lowercase a for Adams since J's are annoying to write. So Unitarian applies to Adams.
that's not the premise.
That's a premise.
Okay, that makes sense.
That's a premise, and it's a premise with a flagged variable, right?
Yeah.
No. John Adams here is not a variable. It's an individual particular person. The same way that 3 is not a variable, it's an individual particular number. Okay. So, no, this is not a flagged variable. It's not a variable at all. It's a particular person. Okay. So now, what's line 3? Do we have one?
No.
No, that's it for our premises. Let's see where we're trying to prove. Let's write that up here, just to remind us where we're trying to get. We're trying to prove that John Adams was not Episcopalian. So we're trying to prove not Episcopalian applies to Adams.
Yeah.
Okay. So line 3 is going to be universal specification on this.
Okay.
Alright? So I say if Episcopalian, maybe put parentheses here, if Episcopalian applies to Y, or Presbyterian applies to Y, then not Unitarian applies to Y, right?
Yep.
But we don't care about an arbitrary Y in this case. We don't care about for some arbitrary person, if they're Episcopalian or they're Presbyterian, then they're not Unitarian. We care about atoms. And so we actually want to say this for the particular atoms. That's still a perfectly valid way we can use universal specification.
Okay.
Remember what the rule of universal specification was. If a formula S results from a formula R by substituting any term, Y, the term we're substituting is little a. I can substitute little a in there. If this is true for anyone, it's true for atoms. Perfect. So that's universal specification on line 1, and this just depends upon premise 1. Now what?
We know that he is, so that's a contradiction.
Not a contradiction.
Oh, we know that EA or...
Remember, if we know alpha implies beta, which is this, then we know not beta implies not alpha.
Yeah, so we know EA and PA.
So I know not this, that's right here. I know not this, therefore I know not this. So I'm able to conclude not being Episcopalian applies to atoms or Presbyterian. I know it is not the case that being Episcopalian or Presbyterian applies to atoms.
Yeah.
This was tautologically implied by lines 2 and 3. And it depends upon, now, both premises 1 and 2. Right? Okay. Now what?
5 is not EA and not PA.
Perfect. We distribute. If I know not alpha or beta, that's the same thing as not alpha and not beta. If I know you don't have a car or a house, I know you don't have a car, and I know you don't have a house. Okay, so that's 5 here. 5, we know not Episcopalian applies to atoms, and not Presbyterian applies to atoms. This is tautologically equivalent to line 4. And so we're still just dependent upon premises 1 and 2.
We just universally generalize.
Remember what we're trying to prove. We're just trying to prove this.
Yes, how do you get rid of that? Should we just say it's not important?
If I know alpha and beta, I can conclude just alpha.
Yeah.
If I know the sun is shining and the sky is blue, I know the sun is shining. So if I know that he's not Episcopalian and he's not Presbyterian, I'm able to conclude, 6, that he's not Episcopalian, applies to atoms.
So
This is tautologically implied by line 5, still using premises just 1 and 2. And that was one of our logical rules. A and B implies alpha. This implies this is a tautology. One of those, I don't know if you remember when we made our list of commonly used logical rules. You all remember that?
when?
2 weeks ago? Or 2 classes ago?
I thought it was the first class.
That seems early. I gave you a list of basically all the rules of logic that we're going to use. It wasn't exhaustive, but it got the gist of them. Like every time I say this is logically equivalent to this, that's a tautology. That's one thing we talked about in that list. Basically, the rules of logic that we listed out there are all the ways that we can use Rule T. Rule T is using our rules of logic.
Yeah, I missed that
Oh,
class. I missed one of them.
well, you should watch the one you missed. Probably help.
Probably, yeah.
Alright. Anyways, and we're done. Square box. Square box, common symbol for, and thus it is demonstrated. Yeah, I showed John Adams is not Episcopalian. Therefore, he was not Episcopalian.
No generalization.
You don't have to use it. You just can use it. Alright. So now, let's do some fun stuff. So that finishes that section. This next scene, the author just left as a homework problem, but it's cool enough and it gives you a great insight for where we're headed here that I want to do a deep dive into this problem.
It's a big problem.
It is a big problem. So, what we're doing here now, this is the first time the author is now giving us an axiomatic system to operate in. And every axiomatic system has 4 parts. It has what we call undefined terms. It has what we call axioms. It has what we call definitions. And it has what we call theorems. Stop writing so much so I can talk. THM. Should just write it. Okay. These are the 4 pieces to any axiomatic system. Every field of mathematics is composed of just these 4 things. Now let's get intuition for each of these things, what they are and why they're crucial. First off, undefined terms. You can't define everything. If I give you a dictionary in some arbitrary language like French, and I ask you, what does this French word mean, and I give you the dictionary, you can look up that French word. And when you look up its definition, what are you going to find?
French.
A bunch of other French words. And then you can go look up all those French words. And what are you going to find?
French.
A bunch of other French words. Now, one of 2 things has to happen here. Well, one of 3 things. Either 1, you end up trying to look up one of the words you were already trying to look up.
Okay.
Right? You're looking up word A, and in the process you come across word B, and in looking up word B, you come across word C, and in looking up word C, you come across word A again. And then you're right back where you started. How did that help you? It didn't. We call that a circular definition. There is a famous example in, I think it was Webster's, in one of their editions, where the definition of a mountain was something larger than a hill, and the definition of a hill was something smaller than a mountain. Thank you. That was very insightful. So that's one case. Either you end up using words you were trying to define to begin with. That's a circular definition. Number 2 is there's an infinite regression and an infinite number of words. That's pretty useless. The third case is that there's going to be words that are used that don't have a definition.
Okay.
And we call those words, those terms, undefined terms. So every axiomatic system has undefined terms. Now, if it's undefined, does that mean it has no meaning? No. The axioms use undefined terms to give them meaning. Axioms are basic assumptions that we start with. So I start by assuming a couple statements, 1, 2, and 3. I assume those 3 things to be true, and they're going to use some words in it that are going to be undefined words.
Okay.
That's what an axiom is. Then we have definitions. Definitions create new words in terms of existing words. So you can take these undefined terms and start putting them in different combinations to create what we call definitions. Definitions are never required in the field of mathematics. We could have always just used these terms directly. A definition is just a way of talking about some combination of these terms in a shorthand way. And then finally, theorems. Theorems are the logical implications of our axioms. Maybe if I know this is true and this is true, putting those 2 together gives me this statement. I now know that's true. And maybe putting this together and this together implies this statement. And maybe putting this together and this together implies some other statement. We call each of those theorems. This is what every system of mathematics is. This is what every system of mathematics is, an axiomatic system. We're going to do a very, very simple axiomatic system here for psychology. Where's my eraser? Behind me. For psychology. And I'm going to give you intuition for what these things mean, but not a definition. So, number 1 here, axiom 1, premise 1, or first assumption. Q here is going to be weakly prefers. That's why I'm going to read that. We'll give you intuition for what this means, but it's just intuition. We're saying for all x, for all y, for all z, if you weakly prefer x to y, and you weakly prefer y to z, then you weakly prefer x to z. We'll think about this as an example. I'll use it as an example over and over again. Food. You're ordering some lunch. If you weakly prefer pizza to a burger, and you weakly prefer a burger to a steak, then you weakly prefer pizza to a steak. Weakly preferred, we're going to think about here just means you'd be willing to take it instead of. If you're willing to take pizza over a burger, and you're willing to take a burger over steak, then you're willing to take pizza over steak. That's what Q here is going to mean.
Willing to take.
Willing to take. That's how we'll interpret Q, to help give us intuition for what this is saying. Strictly speaking here, Q is an undefined term.
Okay.
And what do we know about Q? It satisfies this axiom. But we're going to think about it as weakly prefers, and that's what I'm going to call it. This next one says, axiom 2, for all x and for all y, you either weakly prefer x to y or you weakly prefer y to x. For your lunch option, you're either willing to take pizza over steak or you're willing to take steak over pizza. One of those two has to be true. So these are our two axioms, the two basic things that we're going to assume. Now there's two notions that are going to be useful to have. One's the notion of indifference, and one's the notion of you strictly prefer.
Okay.
So indifference means you can take one or the other. You have no strong preference. So for all x and for all y, if you're indifferent between x and y, if you're indifferent between pizza and steak, that means you're willing to take the pizza over the steak and you're willing to take the steak over the pizza.
Okay.
You weakly prefer the pizza to the steak and you weakly prefer the steak to the pizza. You're willing to take one over the other and the other over the one. That's what we're going to define indifferent to mean. Notice we're defining indifferent in terms of Q here.
Yeah.
We're saying anytime you see x, I, y, you can just replace that with this. This is just shorthand for this.
Okay.
And it just seems to capture a useful concept for us that we want to talk about, like indifference. Next thing we're going to talk about is strictly prefer. For all x and for all y, if you strictly prefer x to y, then that means you do not weakly prefer y to x. Now here's intuitively how you probably want to think about it, and then we'll come back to this. Here's how you'd want to think about it. For all x and for all y, if you strictly prefer x to y, then you would think that means you weakly prefer x to y, and you do not weakly prefer y to x. If I strictly prefer pizza to steak, that means I'm willing to take pizza over steak, and I'm not willing to take steak over pizza.
Yeah. That's saying the same thing twice.
This is saying the same thing twice?
Is it not? Okay. Yeah, it's not saying the same thing.
That's what it means. If I strongly prefer pizza to steak, that means I'm willing to take pizza over steak, and I am not willing to take steak over pizza. That's what it means I strictly prefer pizza to steak. Okay, now notice how we actually define this. We said, if you strictly prefer steak to pizza, that simply means you are not willing to take pizza over steak.
Okay.
Now, why do we define it this way instead of this way? Because from this we can conclude this. Because I already know if it's not the case that you weakly prefer y to x, and notice what axiom 2 here says. This says you always prefer one of the two, either x to y or y to x. And if I don't prefer y to x, then I can already conclude I must prefer x to y. So I can conclude this from this whenever I want. So we don't need to include that piece as part of the definition. Makes sense to our intuition to include it, but to keep our definition as minimal as possible, we don't need to include it. But your intuition should be correct about this. You with me? So basically, we're going to be doing something where I gave you some paragraph. These were always the first 4 statements of your paragraph. And we're going to say, now from these 4 statements conclude this. Now from these 4 statements conclude this. Now from these 4 statements conclude this, etc., etc. These are going to be theorems. So these 2 are axioms here. Notice we never defined Q. This here is just defining I. This here is just defining P. Notice that we never actually need to use I. I could always just use this. It's the same thing as I. And we never actually need to use P. I could always just use this. It's the same thing as P.
Yeah.
They're just niceties. Okay. And so now we're going to start proving a bunch of theorems. We have our undefined term, Q. We have 2 axioms. We have 2 definitions. Now we're going to prove a bunch of theorems. Okay. Strictly speaking, in proving these theorems, I would do line 1 is this, line 2 is this, line 3 is this, and line 4 is this. And then start from there. That's super obnoxious to do that over and over again for each one of these statements. So it's going to be understood that that's line 1, line 2, line 3, and line 4. I'm going to give those lines special names. I'm going to call this A1, this A2, this D1, this D2. And whenever we use them in our proof, we'll just reference them as needed. But strictly speaking, if I were to thoroughly prove each one of these, my first 4 lines would always just be rewriting these things out. And then I'd reference them by line 1, 2, 3, and 4. But instead, I'm just going to reference it by A1, A2, D1, and D2. And we'll start as if we already have those 4. Okay, so proving this one, theorem 1. What are we proving? We're proving for all x, you're always indifferent about your choice between x and x. Makes intuitive sense, right? All right, so let's prove that. Line 1, what do I know?
Definition of indifferent.
Well, definitions just allow me to replace things with things. I'm going to start with this one. Maybe I'll just do the first one to give you a feel for how this goes. So first thing I'm going to write is that for all x, how did I write this here? Let me keep my notation clear so I don't go back and forth. Yeah, that's how I wrote it. And I think that's it. Okay. So my first line I'm going to conclude is that we know xqx or xqx. Maybe give myself more space right down here so I have more space this way. 1. I always know xqx or I know xqx. And I'm saying this comes from universal specification on axiom 2. And this depends for its validity only upon axiom 2. So I took this statement. The statement says I always prefer for any x and y, I either prefer x to y or y to x. I could plug the same thing in there twice and it should still be true. So that's universal specification on line A2. And now we only know this is true if A2 is true. So A2 implies this line so far. Cool. 2. Now, if I know xqx or xqx, what do I know?
XQX.
I know xqx. Perfect. xqx, this is tautologically implied by line 1, and we're still only dependent upon axiom 2. All right, now if I know xqx, what do I know? Remember where I'm trying to get. I'm trying to get xix, right?
Yeah. So
And then universal quantifier.
you know XQX and XQX.
Perfect. If I know xqx, and I definitely know xqx is true, and xqx is true. Right? That would be saying alpha implies alpha and alpha is a tautology. All right? This is tautologically implied by line 2, and we're only dependent upon A2 for our validity. All right, now what?
In general, use the definition.
Now we use our definition. If we have xqx and xqx, we're able to conclude that's exactly what we mean by XIX. This is tautologically implied by 3 and definition, which definition is that? 1. So now we're dependent upon A2 and D1 for our validity. Remember, it's understood that we put these 4 things as our first 4 premises. These are always going to be our only premises for each of the things that we prove here, when it's all said and done. Okay,
Square box.
almost. Now I can universally generalize.
But that's not what we're trying to get. Oh, that's not what you wrote on top of my head.
Oh, I was just saying the next place we're trying to get, sorry. But, yeah, you're right. So now we can conclude for all x, XIX, that is using universal generalization on line 4. And again,
2D1.
none of our axioms were flagged, so we're good. So A2, D1. I mean, none of our premises were flagged. Okay, now square box. Now we're done. So I just already showed these 4 things imply this is true.
Okay.
Next, let's show they imply this is true. Let's make intuitive sense as to what this is saying. This one is saying, if you're indifferent between x and y, you're indifferent between y and x. Makes intuitive sense? Basic rule of thumb, by the way, don't try and prove something until it feels obvious to your intuition.
Yeah.
So think about it until it feels obvious to your intuition, then go and try and prove it. Okay, so again, lines 1, 2, 3, and 4 are those things. So we start at line 5, but we're going to call it 1. And we call 1 A1, line 2 A2, line 3 D1, line 4 D2. Okay, so what am I going to start with for this one?
Axiom 2. Axiom 1.
This one, we're trying to show that this implies this. Right?
Yeah.
So, typically when we're trying to prove an implication, we start by assuming the antecedent.
Okay.
So, we're going to start by assuming the antecedent. So, I'm going to introduce XIY as a premise. That's a premise. And careful, careful. Now these are 5 variables. X and Y are variables. We introduce them in a premise.
Unflagged.
Huh? I'm ultimately going to get rid of this premise. Ultimately, I'm going to show XIY implies YIX. And when I go to that, I'm going to get rid of this as a premise. So I'm going to have XIY dot 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 YIX. Therefore, by rule CP, XIY implies. And then it will no longer be using this as a premise. I'll get rid of my 5 variables and we'll all be happy. So this depends upon 1, and it has 5 variables, X and Y in it.
Okay.
Okay, line 2. If I know you're indifferent between X and Y, what do I know?
You're different between y and x.
That's what we're trying to show. We need to use our definition. What does it mean to be indifferent between X and Y?
X, Q, Y.
That means we weakly prefer X to Y. We'd be willing to take X over Y, and we'd be willing to take Y over X.
Yeah.
Again, that's a premise, or not a premise.
Yeah. Total.
This is tautologically implied by line 1 and
Definition 1.
definition 1. So now this is dependent upon 1, together with the 5 variables X and Y. This is dependent upon premise 1 and definition 1 for its validity. Okay, now what do we know?
Because we know Q, we don't know that. We know that X, I, Y is true, so we know both those are true. So we know Y and QX.
Plot the order here.
We also know that.
YQX and XQY. And that was another one of the things we proved. Alpha and beta, we showed that's tautologically equivalent to beta and alpha. So this is tautologically equivalent to line 2, and its premises are the same as the line above. Okay? Now, for
y-i-x.
this is y-i-x by definition. That is tautologically implied by 3 and definition 1. And again, it's just depending upon these things for its validity. Same as lines above. Right? Now I showed if this is true, then this is true. So now using rule CP, I can say 5, therefore xiy implies yix. This is using conditional proof from lines 1 to 4. And now I am no longer dependent upon premise 1. So now I'm just dependent upon definition 1 for this to be true. Right? And now we can universally generalize. That's universal generalization on line 5, and it's only dependent upon definition 1 for its validity.
Yep.
And square brackets. Okay, let's prove the next one. Let's see, what were we on, 3? What does 3 say, intuitively? If you're indifferent between x and y, and you're indifferent between y and z, then you're indifferent between x and z. Or in other words, indifference is,
Associative.
no,
Commutative.
no,
Distributive.
no.
It's only 3.
Going back to our properties of relations,
Transitional.
transitive.
Transitive, that's the word.
It's transitive, that's what we're proving. Okay, so what are we going to start with?
Premise.
We're trying to prove an implication. How do you typically prove an implication?
Yeah, so
Assume the antecedent and show that leads to the conclusion.
premise of x, I, y.
Yeah, so we're going to introduce xiy and yiz as a premise,
with 3 flag variables.
and it has 3 flag variables. So 1 has flag variables x, y, and z. Okay, now plugging in our definitions. 2, this gives me xqy and yqx. And you put parentheses so we can keep track of where that came from. That's from this one. And then we have and yqz and zqy. Move that P over. Okay, this is tautologically implied by line 1 and definition 1. So now this is dependent upon 1 with x, y, and z as flag variables, and definition 1 for its validity. Okay, now we're going to use associativity and commutativity for and. Associativity basically just enables us to move around the parentheses, and commutativity enables me to change the order. In other words, I know this is commutativity, and then associativity is if I know A and B and C, that's logically equivalent to A and B and C. That's associativity. So that just tells us we can change the orders and put the parentheses where we want. So 3, regrouping these. I'm going to do xqy, we'll keep that one, that's right there. yqz, I'm going to bring that one over and group it with this. yqz. And ZQY, I'm going to put that right here. And YQX, I'm going to put that right here. This is tautologically equivalent to line 2, and it's dependent upon the same lines for its validity. This is logically equivalent to that line. We just change the orders of things. Right? Okay, now what are we going to do?
X, I, Z.
If I know that you weakly prefer X to Y, and you weakly prefer Y to Z, then I know what?
We prefer X to Z.
I weakly prefer X to Z. That was axiom 1. For all X, Y, and Z, if you weakly prefer X to Y and you weakly prefer Y to Z, then you weakly prefer X to Z. So from here, this, we can conclude XQZ. And from this, I can conclude
ZQX.
ZQX. For the same reason. So now, this is tautologically implied by 3 and axiom 1. And now we are dependent upon 1 with its 5 variables, X, Y, and Z, axiom 1, and definition 1. Okay. Now, XQZ and ZQX is the same thing as what?
Just X.
If I'm willing to take a burger over fries, and I'm willing to take fries over a burger, then I'm indifferent between a burger and fries.
That's definitely the difference.
So that's the same thing as indifference, XIZ. And this is tautologically implied by 4 and definition 1. So now this is dependent upon, oh, same thing still. We already used definition 1 earlier.
Yeah.
Okay, so now what did I show? I showed if we have this, then we can include this. Or in other words, this implies this. So now I know, maybe put parentheses, XIY and YIZ implies XIZ. And now, that's conditional proof from lines 1 to 5. And now I can remove premise 1 as a premise. And so now this is only dependent upon A1 and D1. Once again, it's only dependent upon these 4 statements. Only 2 of the 4, but who cares? The point is, if you know those 4 statements are true, you now know that this is true. Oh, and it universally generalized. Now we can universally generalize. So 7, now I can conclude, for all X, for all Y, for all Z, if you're indifferent between X and Y, and you're indifferent between Y and Z, then you're indifferent between X and Z. And end it. And this was universal generalization on line 6, and it's only using A1 and D1. And we're done. Little black box. Good? All right. Next one. Which one are we on? 4. What does 4 say? If you strictly prefer X to Y, then you do not strictly prefer Y to X. If you have to have steak instead of pizza, then you're not willing to have pizza instead of steak. All right, let's prove that one.
Okay.
Huh?
Yeah.
So what's the first thing we do?
Axiom 2. No, 1.
What kind of statement are we proving?
An implication, so assume the antecedent.
Assume the antecedent. When you're proving an implication, always start by assuming the antecedent. It's almost always the right thing to do. The right thing to do? It's almost always the thing that I do. Not sure there's a right or wrong way to prove, but it's what makes the most sense to me. So I always start by assuming the antecedent. And I'm going to indent it because I know, hey, down the road I want to get rid of this thing as a premise. So assume that you prefer x to y. This is a premise, not sure how big these will get. Try and leave more space this time. This is a premise, only dependent upon itself with flag variables x and y. Okay. Now what?
Should we split up part by definition 2 that?
Yeah. Remember what I told you in discrete math? Step 2 is always unravel your definitions. That's the same thing as doing this. Plug in your definition for P. So, what does it mean for you to strongly prefer x to y?
You don't
It means you do not weakly prefer
like x.
y to x. If you strongly prefer pizza to steak, you are not willing to take steak over pizza. This is tautologically implied by 1 and definition 2. And so now it's dependent upon 1 with flag variables x, y, and d2 for its validity. Okay, now what?
Now,
Maybe it'll help us to think where we're trying to get. So we're on this one, right? I'm ultimately trying to get not ypx. Just put this as scratch work over here. But what is not ypx? That's the same thing as not xqy, right?
so what is x cubed y?
Which is the same thing as xqy. So ultimately we're trying to get an xqy.
So we use the back contradiction. That's
No.
the back.
What does axiom 2 say? Axiom 2 says I always either weakly prefer x to y or y to x. Well, I know I don't prefer y to x, so I must prefer
X to y.
x to y from axiom 2. Perfect. So 3, I can conclude then I must weakly prefer x to y. This is tautologically implied by line 2 and axiom 2. And now this is dependent upon 1, axiom 2, and definition 2. Okay, so now following our thinking here, remember where we are trying to get. We're trying to get here. We'll know we've gotten there if we can get here, and we'll know we can get here if we can get here. Well, we're here, so now we just need to go here.
Okay.
That's some scratch work we did this one. 4. This is the exact same thing, the law of double negation, as not xqy. This is tautologically equivalent to 3 and depends upon the same things for its validity. Okay? And now, by definition, that is ypx. So 5 is not ypx. That is tautologically implied by 4 and definition 2, and still just depends upon the exact same things for its validity. Right? Okay, now what?
Now we get conditional proof.
Conditional proof. Perfect. So 6. Now I'm able to conclude if this is true, then this is true. So I'm able to conclude, put down a little, xpy implies not ypx. Did I put in parentheses when I wrote there? No, so we'll just get rid of them. xpy implies not ypx. This is using conditional proof for lines 1 to 5. And now we're only dependent upon axiom 2 and definition 2 for our validity. And then what do we do?
We universally generalize.
Perfect. Then we would universally generalize right here, and then we'd be done. All right, let's try 5. 5 is going to be a bit harder. Okay, number 5. What are we trying to prove? We're trying to prove that strict preference is transitive. If you have to have pizza over a burger, and if you will only take pizza, if you strongly prefer pizza to a burger, and you strongly prefer a burger to fries, then you strongly prefer pizza to fries.
Yeah.
If you say pizza is always better than a burger, and a burger is always better than fries, then you're saying pizza is always better than fries. Okay. So that's what we're trying to prove. Strict preference is transitive. How are we going to start?
By, yeah, we're gonna assume the
An
antecedent.
implication, so pretty safe to start by assuming the antecedent. So x, p, y, and y, p, z. That is a premise, and it only depends upon itself with 5 variables, x, y, and z. Right? Okay, now what?
We know that x, p, z through a1. Oh, we're gonna unravel definitions first.
Unravel definitions, yeah, plug in your definitions. The reason you always want to unravel your definitions is you want to get things back in terms of Q's so you can use your axioms. Because your axioms only apply to Q's. So it's typically a good rule to start by replacing your P's and your I's with your Q's. So replace our P's with Q's because then we can use our axioms because our axioms are about Q's. They're not about P's. All right. So in terms of Q, what does this say?
Says not y, qx, and not qyx. X, qy.
And not Z, Q, Y.
Z, qy, yeah.
If you strictly prefer X to Y, then you're not willing to take Y over X. And if you strictly prefer Y to Z, then you're not willing to take Z over Y. Okay. So that is tautologically implied by lines 1 and what definition? 2?
Yeah.
And definition 2, this is dependent upon 1 with 5 variables X, Y, and Z, and definition 2. All right, now what? A lot of wind.
There it is. A1.
Yeah, now we're going to use axiom 2.
Y2. There's no order.
If you don't weakly prefer Y to X, then you must weakly prefer,
X to y.
and if you don't weakly prefer Z to Y, then you must weakly prefer
Y, z.
Y to Z. So 3, that means we must weakly prefer X to Y, and we must weakly prefer Y to Z. That's tautologically implied by 2 and axiom 2. And now we're dependent upon 1 with X, Y, and Z, definition 2, and axiom 2. And I need to write smaller because we're going to have a few more lines. Tautologically implied by 2, we need 2. Okay. Now what?
Now x, axiom 1, x, qz.
Okay, we know XQZ. Where would you go with that?
I don't know.
So let's see where we're trying to get. We're looking at 5, right? We're trying to get XPZ, which is the same thing as not ZQX.
So we're on the right path with that.
So we get XQZ, that's true, but we're trying to get that ZQX is false.
You can get that from A2.
No, you can't. A2 tells us one of them is true. They could both be true, it just tells us one of them is true.
Strict exclusive words.
Now, I don't know how to give you intuition for what I'm going to do next. This is just what I do when I get stuck.
Okay.
I try proof by contradiction. If I can't figure out how to get that stupid statement, I try to think, can I work with the negation of that statement? Which is XQZ. That I can work with.
Okay.
So, I'm going to introduce now as another conditional premise. It's a conditional premise inside a conditional premise. One that I'm promising later I'm going to get rid of. The negation of what we're trying to get. I'm going to assume not. And we'll indent it even further. I'm going to assume not XPZ. I'm going to introduce that as a premise. And once again, this is using 1 with X, Y, and Z flagged. This is using 4 with X and Z flagged. And D2 and A2.
Why is it using D2, A2, and 4 and 1?
Because it's not. Thank you. This is only its premise. It's only dependent on self-first validity with 5 variables X and Z. Good. Sorry. Okay. Now let's unravel definitions. What is XPZ? So we have not. XPZ is what?
Yes, Y, Q, not Z.
It's not ZQX, right? So just take that piece and replace it with this definition. This is tautologically implied by 4 and definition 2. And now this is using 4 with 5 variables X and Z and D2. Okay. Now not gives me
Yes.
is. So now I have ZQY. Or ZQX. Thank you.
G5.
That's tautologically implied by 5 and nothing. It's tautologically equivalent to 5 and depends upon the exact same premises. Right?
Yeah.
Where was I going with that? Assume not XPZ, which gives me ZQX. Oh, I can combine it with one of these to get the negation of one of those. Okay, that's what I'm gonna do. So 7 here, I'm gonna look at ZQX, and let's see, what do I want to AND it with? I'll AND it with this. You'll see why. If I AND this with this, what am I gonna get? If I know ZQX and XQY, then I know,
ZQY.
then I may get ZQY. But now, look at what this says. Not ZQY. ZQY and not ZQY is going to be my contradiction. So that's going to be my contradiction. All right, so this was tautologically implied by 6 and 3. Is that where that came from? Yes. 6 and 3, so now we're dependent upon premise 4 with 5 variables X and Z, definition 2, and what were we dependent upon in line 3? We were dependent upon premise 1 with 5 variables X, Y, and Z, D2, we already have that listed, and then axiom 2. Right? Okay. So now 8, we're going to conclude ZQY. This is tautologically implied by 7 and axiom 1. And now this is dependent upon, let me write these in better order, premise 1 with x, y, and z is flagged, premise 4 with x and z is flagged, axiom 1, axiom 2, and definition 2 for its validity. Right? And now 9, I know ZQY and not ZQY. This is tautologically implied by 8 and 2. And this is still dependent upon all those same things. So then, line 10, I can conclude not this thing. So then I know XPZ, and this is by reductio ad absurdum, from lines 4 to 9. Just so you know, the way that we would do this in a math proof, this is the line where we say assume by way of contradiction, and then this would have been the line where we put the double arrows. Okay. So now this is just dependent upon, we removed premise 4 as one of our premises. So now this is 1 with x, y, and z, axiom 1, axiom 2, and definition 2. So I just really showed that if you strongly prefer x to y and you strongly prefer y to z, then you strongly prefer x to z. I showed this being true implies this is true. So 11 now, we get rid of our index completely. We showed xpy and ypz all together implies xpz. This is using conditional proof from line 1 all the way down to 10. And now this is only dependent upon axiom 1, axiom 2, and definition 2. So once again, and then universal generalization. And we're done. Right? So there's another statement that we proved is true if our 4 starting statements are true. If we have those 2 axioms and those 2 definitions, then we can conclude that. I'm just under that. You still getting value out of doing these, or you think we're good?
I think I have it down as much as I can.
I think you have it down as much as you can. Because the next 2 also fall from this.
I have the idea of it down.
And so that's the first time that we're getting a view, a big picture of what we're after here. Because this is exactly what every axiomatic system is. And so when you start developing arithmetic, you start with, I think there's 8 axioms of arithmetic, so you have 8 of these. And then definitions you can create along the way as you go. You can create a definition for anything you want.
Yeah.
So eventually we would, our axioms, 2 things that are undefined in terms of arithmetic, are plus and multiplication. Use a dot for multiplication. Those are 2 operations that aren't defined in arithmetic. But we can define subtraction, and we can define divided by. And we use plus to define subtraction. What does it mean to do A minus B? By definition, that means A plus negative B. Or what does it mean to do A divided by B? By definition, that means A times 1 over B. So that's an example of some of the definitions we create. We prove all sorts of things in arithmetic. That's what all you do in an arithmetic course. Everything you did in algebra, you go back to any algebra problem you were given, they would say something like, solve for x. They give you something like, I don't know. We'll do a really simple one. 4x plus 7 is equal to 15. Solve for x. What they're really asking you is to prove that if this is true, then, and find the conclusion that you can come to from this. And the conclusion is then x is equal to 2. And your job in arithmetic is to show that this tautologically implies this together with the axioms of arithmetic. And you use the axioms of arithmetic as you do this. And all the theorems that you prove. So that's one of the systems that we will develop further in this class, is specifically one for arithmetic, to jump ahead where we're going. But the reason I wanted to develop this one is because it's a nice simple one with just 2 axioms, just 2 definitions, and it starts to give you a sense for what a theorem is. And by the way, it's the same thing you do in geometry. Geometry, you start with, if you remember all the way back to what we were doing, you both did philosophy, right? You didn't? Euclid's Elements, just for you then. We started out by, Euclid gave us his 5 common notions, 1, 2, 3, 4, 5, and his 5 postulates, 1, 2, 3, 4, 5, and then he had a whole bunch of definitions that he listed out. And that's how the book started. And then he starts proving things from those. His common notions and his postulates are the same things as axioms. And then his definitions are the same thing as definitions. And all Euclid's Elements is just doing this exact same thing. Now Euclid is further back, so he didn't have the same precision that we have in modern times. But the thinking is identical. So it's what every axiomatic system does. Classical mechanics. You're talking about your first physics class that you would take. Your axioms are Newton's laws. Axiom 1 of Newton's laws, or his first law of motion, is that there exists a reference frame such that in that reference frame, if an object is experiencing a net force of 0, then its acceleration isn't changing. That's his first axiom, his first law. Then we create our first definition in the system. We say an inertial reference frame is a reference frame where the first law holds. And then Newton's second law is basically F equals ma. The acceleration an object experiences is proportional to its mass times its acceleration. That's his second law. And then his third law is, if object A exerts a force of F on object B, then object B exerts a force of negative F on object A. So those are your 3 axioms that you use when you're developing classical mechanics. And you start saying if these things are true, what else is true, what else is true, what else is true. And along the way you create definitions. So you define, oh, you don't have calculus. Hard to talk about physics without calculus. But you define velocity to be the derivative of position with respect to time, acceleration to be the derivative of velocity, it doesn't matter. You just start defining terms as you go, defining what you mean by these things. But those are your assumptions. You create your definitions as you go. And you develop the system of classical mechanics. So every systematic body of knowledge is an axiomatic system. It has its axioms, even though you may not know it most of the time. Has its definitions, has its undefined terms, and then it has all the theorems that it proves. And the amazing thing is now you know that if you're in some circumstance where these 4 things hold, then you instantly know all these things for free. Because this doesn't just have to be weak preference. Another thing we could have replaced this Q with is this symbol. Less than or equals. Less than or equals. Less than or equals. Less than or equals. We still could define y the exact same way, or I the exact same way, and we still could define p the exact same way. Oops. Now, thinking about it intuitively, the way you know less than or equals, is it always the case that if x is less than or equal to y and y is less than or equal to z, x is less than or equal to z? Yep. Is it true that you either have x is less than or equal to y or y is less than or equal to x? Yeah, that's always true. X is always less than or equal to y, or y is less than or equal to x. That's always the case. Okay, define I this way, who cares what it's saying. Define P this way, who cares what it's saying. Then you know all this for free. It doesn't change anything. We just go through and replace our Q's with our less than or equals, and it still holds. And there could be other interpretations that we apply to this. And as long as our interpretation satisfies these two things, these two axioms, then we get everything else for free. And that's the powerful thing about building these systems. So for Euclid's element says, if these 10 postulates are true, or these 5 common notions and these 5 postulates are true, then all of these, and he proves almost 500 theorems. And so we go out in our real world and we start testing those things. One of his postulates are that any 2 points defines a line segment. Does that seem to be true in our space, that if I have 2 points, I can create a line segment between them? Yeah, that seems to be true. What's his next one? It's if I have a line segment, I can extend it indefinitely. Does that seem to be true in our universe? Yeah, that seems to be true. Next one says that if you have a line segment and a point, that defines a circle. Does that seem to be true in our universe? Yeah, that seems to be true. What am I missing? Oh, all right angles are congruent. Does that seem to be true? If I got a right angle over here and I go and I compare it to a right angle over there, are they the same? Yep, that seems to be true.
Yeah.
His last one is basically the parallel lines one. If I have a line and a point not on the line going on forever, does it seem to be true that there's only one line I can draw through this point so that they never intersect?
Yep.
In other words, if I draw a slightly different line, will they eventually intersect?
Yep.
Yeah, that seems to be true. Okay, then all the 500 things that Euclid proved, we get for free in our universe. So that's the power of these systems. And that's the beauty of developing logic. It gives you the foundations to start developing these axiomatic systems. So that's big picture where we're going. And now we'll go back and do proofs more like what we were doing earlier. And not a system as involved in this for a little bit. But just want to do a deep dive into it to give you a good taste of where all this is going. And start you with a small system before we jump to a big one like arithmetic, which starts out with 8 axioms instead of just 2. Any questions about that? This is where I plan on ending it for today, so. Good? All right, we'll end the recording there.